Good afternoon. So we'll move on from where we stopped in the last class. So let me quickly correct something. Someone called my attention to what we actually solved here. Of course, the answer is correct. That's the correct answer. We missed out these square roots. Okay, we missed out including the square roots from this point. Okay, so this square root was here. It didn't disappear. So square root still here, square root still here. So that is it, square root. Then this also, the square root still here. So when you make the substitution, this will be 0. Square root of 1 is still 1, so you get 2. So that's that about that. Alright, so I guess we are good to go. We are good to go. So we'll pick some more problems and solve. Then we will look at today's concepts. Okay. So you remember we talked about limit of polynomials like this form. Okay, whereas we said that it is the highest power of the polynomial that determines the limit. Okay, so we saw that. Let me quickly point out something here that can help you. So look at this example, for instance. This question, for instance, we have limit of 3x cubed minus x squared plus 2. We have this problem, limit of 3x cubed minus x squared plus 2 as x approaches infinity. So you want to find out this limit as x approaches infinity. So we already saw, and correctly so, that the limit of polynomial like this, okay, is simply given by or determined by the highest power of the polynomial. As this the term carrying the the highest power term of the polynomial is what determines the limit. So in this case, I can simply say that this limit is equal to 3 into, just substitute into what I have here. That means I'm dealing with the highest power only, this raised to power 3, which is going to be simply infinity, and it's fine, it's correct. Okay, so another way you can visualize this is to see this as being equal to the limit as x approaches infinity. If you decide to factorize, for instance, you're going to have this to be 3x cubed. As if you move out 3x cubed from all the terms, you're going to have 3x cubed into 1 minus, what you have left here will be x squared over 3x cubed. That's going to be minus 1 over 3x. Hope you got that. Plus 2 over 3x cubed. So that's going to be what you have as x approaches infinity. And if you like, if you substitute into this also, you're going to get the same thing. When you substitute into this, everything here is going to become 0. Okay, this is going to be 1 over infinity, which is 0, 2 over infinity, which is 0. So that one is gone. So you have just 1 here. So what you have at the end of the day is simply equal to the limit as x approaches infinity of 3x cubed multiplied by 1, which is still 3x cubed, which is still infinity. So anyhow you approach it, you are fine. Okay, so that is that about that we talked about. Okay, then I guess you should be able to solve the other problems here by now. So there's a particular one I think most of you are missing out on. Look at this, number 1 and 2. Look at number 1 and number 2. Let's quickly look at how to solve them. Number 1 says, number 1 is limit of limit as x approaches 0, as x approaches 0 of 1 over 3 plus 2 raised to power 1 over x. Okay, and the second one, which is number 2, is limit as x approaches 0 of 1 plus 2 raised to power 1 over x divided by 3 plus 2 raised to power 1 over x. So that is that about that. Right, so we want to find out what the limit of this is. Now naturally you are tempted, or you'll be tempted to just make a substitution into this, okay, which will not give you the exact picture or the correct picture. Okay, so the first thing you should notice is that this is the only portion that actually determines this limit. Every other portion is some constant, so this is the only portion that determines the dependence on x. So then you have to be careful with this portion. As a matter of fact, you know, or you should know, that the limit of this is simply plus infinity from above and minus infinity from below. From what we have done previously, you know that the limit of 1 over x does not exist. Okay, and then if you like, you can actually say that, naturally you can say that this limit of this function, you can say this is equal to the limit as x approaches 0 of 1 over 3 plus 2, or you can simply say, let's leave out this now, 3 plus 2 raised to power the limit as x approaches 0 of 1 over x. You can have something like this, because the limit of this is not affected. This is constant, this is constant, so the only thing that determines the limit of the entire function is the limit of what we have here in this power. Alright, so so in this case, you're going to also regard this as piecewise around 0. Okay, so because it is piecewise around 0, you know what I mean by that. Piecewise in that when you approach from above, it's going to have a different value from when you approach from below. Okay, so because of that, we'll write it like this: the limit of 1 over 3 plus 2 raised to power 1 over x as x approaches 0 from above. So we look at what happens as x approaches 0 from above. So this is going to be equal to, we know that as x approaches 0 from above, this is going to be plus infinity. Okay, so this is just going to be 1 over 3 plus 2 raised to power infinity. Why? Because as x approaches 0 from above, 1 over x approaches infinity. So 2 raised to power infinity is infinity. So what we have here is simply 3 plus infinity, which is still infinity. 1 over infinity is 0. So that is the limit of this function as x approaches 0 from above. Then again, we consider the second portion. We say the limit as x approaches 0 from below of 1 over 3 plus 2 raised to power 1 over x equals, in this case, as x approaches 0 from below, our 1 over x approaches minus infinity. So this is just going to be 1 over 3 plus 2 raised to power minus infinity. This is going to be 1 over 3 plus, 2 raised to power minus infinity is 1 over 2 raised to power infinity. Okay, so this is just going to be equal to 1 over 3 plus 1 over infinity. 2 raised to power infinity is infinity. 1 over infinity is 0. 3 plus 0. So what you have here is 1 over 3. So as you can see, limit as x approaches 0 from above is equal to 0, whereas the limit as x approaches 0 from below is equal to 1 over 3. So we write that since limit, okay, as x approaches 0 from above of the given function f of x is not equal to the limit as x approaches 0 from below of the function f of x, then the limits of f of x as x approaches 0 does not exist. So that is the solution. That is the way to solve this kind of problem. Alright, so with this I think you can solve this now. So let's quickly do that together. If you look at the second one, this is the number one problem right there. If you look at the second one also, so because this is the limit of this does not exist because it has different values, depending on the sides. So we're going to evaluate the limit in pieces also. So we take the first piece. So first write this out. Limit, we're interested in the limit as x approaches 0 of 1 plus 2 raised to power 1 over x divided by 3 plus 2 raised to power 1 over x. Okay, so we write that the limit as x approaches 0 from above, okay, of 1 plus 2 raised to power 1 over x divided by 3 plus 2 raised to power 1 over x is simply equal to 1 plus 2 raised to power, so as x approaches 0 from above, 1 over x approaches infinity, so this is going to be 2 raised to power infinity, then divided by 3 plus 2 raised to power infinity. So in this case, basically you are going to get infinity over infinity, which is indeterminate. So you cannot proceed with the solution that way. So another thing you can do is to divide through, okay, like we have done in the past. So you can make a division all through and see what it gives you. Sorry. So when you do that, right, when you proceed with this now, you're going to get so this is going to give you infinity over infinity, which is indeterminate. Alright, so this one is indeterminate. So suggesting that we will have to take another approach. So how else can we solve this? So if we decide to divide by the power, you decide to divide all through by 2 raised to power 1 over x. So what is going to happen if you do that? So we can see that this limit is equal to the limit as x approaches 0 from above of, so we want to put this now, so we are dividing all through by 2 raised to power 1 over x. So I'm going to have 2 raised to power minus 1 over x. I hope you know how I came about that. That's 1 over 2 raised to power x is the same thing as 2 raised to power minus 1 over x. Okay, so plus 1 and divided by the same thing here. I'm going to have this to be 3 multiplied by 2 raised to power minus 1 over x. Okay, then I'm going to have this plus 1 also. So that's the limit I have here. So as x approaches 0 from above, this is going to approach, this is going to approach infinity. So I have 2 raised to power minus infinity, which is 0. Okay, here also I'm going to have infinity, so I'm going to have 2 raised to power minus infinity, which is 0 also. So at the end of the day, I have 0 plus 1 into 0 plus 1. Okay, so this is going to give me 1. So this is going to be 2 raised to power minus infinity plus 1 divided by 3 into 2 raised to power minus infinity, plus 1. So this is going to give you 0, and this is going to give you 0. So with that, we have 1 over 1, which is 1. So that is the limit as x approaches 0 from above. you can check that with your calculator to be doubly sure. So let's quickly put this in radian for radian. Okay, so if you enter the function 1 plus 2 raised to power 1 over x divided by 3 plus 2 raised to power 1 over x. Then you calculate. You want to calculate as x approaches 0 from above. So can use something like this. So it's still giving us error. So calculate 0.01, for instance. It's gonna give us 1. Okay, so you have an idea what we're talking about. That's from above. Okay, then we also do it from below and see if it also gives us 1. So we'll find out the limit of 1 plus 2 raised to power 1 over x divided by 3 plus 2 raised to power 1 over x as x approaches 0 from below. So this is going to be, so as x approaches 0 from below, it's quite obvious this is just going to be approaching minus infinity. So what I have here is going to be 1 plus 2 raised to power minus infinity divided by 3 plus 2 raised to power minus infinity. So this will be 0 and this will be 0. So at the end of the day I have this to be 1 over 3. So as you can see now, where the limit as x approaches 0 from the right, that's from above, is 1. This limit as x approaches 0 from below, that's from the left, is 1 over 3. They are not the same. So we write our final answer. We see that is the limit of the given function f of x as x approaches 0 from above is not equal to the limit of the function as x approaches 0 from below. Then the limit of the function as x approaches 0 does not exist. So that is that about that. Alright, so you can check that right here. We calculate, let's put minus 0.001 for instance. We're going to have 1 over 3. So it confirms that the limit from above is not the same as the limit from below. Alright, I guess that is that about that. So always have that in mind when you come across questions like this. Okay, so I think we've solved majority of the problems here. You should be able to deal with them by now. Okay, you should be able to deal with them by now. If there are others you think we should solve together, let me know. So I'm going to I'm going to send solutions, okay, of everything. We'll put everything together and send it to the group so that you have all the solutions with you. I guess this is as simple as it gets. Okay, so we have a problem at hand that there is no solution, or I have not gotten a satisfactory solution to it yet. The one I sent to the group the other day that I asked you to solve, I find it here now. Where did I put this thing? I can't locate that right here. Dingo. Let me check for it. I can't locate where I wrote this question, but I think it's something like this. So whether it is this exactly this or not, you should understand how to solve it. That's the point. Okay, so it's on the group. I showed you this on the group that I was going to provide solution to it in the following class. Okay, So some of you solved this, but I'm not so comfortable with your solution. Okay, so let's see how we can solve this kind of problem. Naturally, from what we have learned so far, of course, naturally you can use L'Hopital's rule, L'Hopital's rule, but we have not done that at this stage. Okay, and then there may be questions, as you have seen in the one I sent to you and some of the past questions. You will see that there may be questions where you are specifically restricted from using L'Hopital's rule, so you don't have any option than to look for other means of solving the problem. Okay, and then I told you about the use of table of values. The use of table of values, though, is a standard method in that it is presented in standard calculus textbooks, advanced calculus textbooks, but because the lecturer has not so presented it, or he didn't make mention of it, you should just know it as some form of check. That is exactly what we do when we use calculator to check. Okay, so you should know it as a form of check for your solution, if your solution is correct or not. Okay, that is when you have gotten an answer, you want to check what's it from the right and from the left and see if it's exactly what you've obtained. Okay, so that is one. Another thing is, if you are actually given a problem and if you are given something like this, for instance, and no method is specified, please don't use table of values unless you cannot think of how to solve the problem using any of the other means you have been taught in class. That have been presented in the school lectures. I hope you got what I said. You should, or you can use table of values if and only if you cannot think of, or you don't have a way around solving that problem using any of the methods you have been solving in class. Okay, so that means when you come across a problem, the first thing that should come to your mind is how to solve it using the methods you have been taught in class. Basically, all the methods we have learned so far have actually been presented in class, okay, except for the table of values. Okay, and you should know the purpose of my presenting it that way. Now, it is because I want you to appreciate what the limit actually is and how you can evaluate it with your calculator. So that is the idea with that. Okay, so you can use that when you see that you don't have any other way you can solve this using any of the other standard methods. Why am I advising that? Because if you cannot solve this using any of the other methods, that means you are going to get 0. Okay, at least using table of values will prevent you from scoring 0. You cannot score 0. Even you can get, it's either you get a full mark, okay, for getting a correct result. Of course, you're going to get a correct result anyway, or you get some marks less than the full mark for using a method the lecturer or the whoever is marking it does not recommend. Okay, they understand what the method is. Nobody who has learned limits would not know what that method is. Okay, but for using a method they do not recommend, you may get less than the full mark. Okay, so that is why it is advisable to use that table of values if and only if you don't know how to do it using other methods, okay, which in this case I call quote standard quote methods. Okay, so that is it. So we want to solve something like this. Now we're not using table of values. Alright, so now you may be tempted to do something like this. Now, recognizing that this is some sign, and you know that for instance you may be even given in the question that given that limit of sine x over x as x approaches 0 is equal to 1. You may be given, you may not even be given, you are expected to know this offhand. So even if you are not given this, you can actually use it to solve a problem. Okay, you can impute it or impose it on a problem solution and get the correct answer. It's fine. Okay, so you want to get the limit of this function as x approaches 0. So number one thing you may be tempted to do is to say you want to divide all through by x. Okay, which is not bad. Okay, you will get to see why that will not be correct as we proceed. If you divide all through by x, why are we dividing all through by x? Okay, normally you want to make this in a form that gives you sine x over x. So since this is sine x all squared, you know sine squared is sine x all squared, you may be looking at having these as sine x over x all squared. So, and you can achieve that when you divide all through by x. You know, when you divide all through by x, and getting into this square root is going to become it's going to be equivalent to dividing all through by x squared. Okay, so you may be tempted to, now this is not correct, but you may be tempted to do it this way and say that this is divided by, you know, square root of x squared, which is fine. Okay, and you maybe then you say also, you know, you have to do the same to the denominator. So you're going to have something like this: 6x cubed plus 4 sine square x. Okay, so you have this, everything under the square root. Then you want to divide by another square root of x square. Alright, so when you do this, you naturally, you should not have a problem, but this is where you have a problem. You may want to think that the square root of x squared is x, and when you do that, we're going to have this as 8 divided by, you know, this is going to be, you know, from your rules of indices, you can just use a single root when you are dividing. Is the rule of sorts now. Alright, so you may be tempted to say, of course, this is correct. In this case, you write that this is equal to this over x squared plus 4 sine square x all over x squared. You know, you are dividing all through. When you open this, when you simplify this, okay, so this is fine. You may then proceed to say that this is 8 divided by square root of 6x cubed over x squared is 6x plus 4 into sine x over x all squared, which is fine too. Okay, so this is limit. So I'm interested in the limit as x approaches 0. So we put limit. This is equal to the limit as x approaches 0, and so this is equal to the limit as x approaches 0 of this. It's fine. Then you may want to say, okay, when you go this way, the limit of this as x approaches 0 is 0. The limit of this is still 8. Then the limit of this is going to be sine x over x as x approaches 0 is 1. So this is going to be 1 raised to the power 2, which is still 1. Okay, you'll be fine. You get your result. I think that's going to give you 4. Okay, so when you do that, you're going to get 4. But now when you check with your calculator, you are going to see that this is not true. This will not be this will be fine for limit as x approaches 0 from above, but it will not be so for limits as x approaches 0 from below. Now, why is this so? The reason is you have missed out something very vital, which I talked about in the last class. It is the fact that square root of x squared is not, it is not the same thing as square root of x all squared, and it is not x. See, they will only be the same if you have x to be positive, that's if x is some number greater than 0. Okay, why are we saying this? If you have something like minus 3 all squared is 9. Square root of 9, okay, naturally or ideally should be plus or minus 3. I've told you at the beginning of this course that we're dealing with calculus, and when we're dealing with functions, we usually say that the function should actually give a single result, so it should give us a single result for a single input. Okay, so there's no how you can have f of x to be two different values. So because of that, we usually stick with the positive value whenever square root operation is carried out. Okay, you can remember that we talked about that before. So in calculus, we do not recognize this as plus or minus 3. No, we do not recognize it as plus or minus 3. In calculus, we do not recognize this as plus or minus 3. In calculus, square root of 9 is simply 3, because we want to get a single value, so we will always stick with the positive value whenever square root operation is concerned. Okay, so you can see now that we started off with minus 3, and now we've arrived at plus 3, which tells us that the square root of this this is to tell you that the square root of minus 3 all squared is actually not equal to minus 3, as you can see here. So the proper thing, which we talked about in the last class, which is the correct thing, is that square root of x squared is actually equal to the modulus of x. Okay, we've talked about the modulus function when we dealt with piecewise function in the past. So if you still don't understand what this means, you can revise that video. Alright, so why? Of course, as you can see, square root of minus 3 all squared is simply 3. Modulus of minus 3 is 3. Okay, if it was a positive number, it will give you that positive number, and that will be fine. So please don't forget this whenever you are dealing with operations involving square roots, involving fourth root, involving sixth root, and so on and so forth, involving any even roots generally. So because when it involves even roots, this is going to always obtain. So when even roots are involved, please bear this in mind, that when you are dealing with square root of x squared, it is not x. Fourth root of x squared, or x raised to the power 4, as the case may be, is not x. It is simply the modulus of x. Okay, so I guess that is clear now. So then, what is the proper way to solve this problem? Bearing this fact in mind. So we're going to start on a fresh page now. So we want to solve the limit of 8x divided by 6x cubed plus 4 sine square x, okay, as x approaches 0. So we say, of course, when you do a direct substitution, by direct substitution, this is going to give you 0 over 0, which is indeterminate. Okay, that is indeterminate, so there's no going further from that. All right, then we have this. So for us to proceed now, we say that we want to simplify this. So this is going to be equal to the limit as x approaches 0 of, so we can have 8x, then we can actually factorize. We can bring out x squared from all of this. Okay, so I can write this as square root of x squared, that's when I bring out x squared, into 6x plus 4 sine square x over x squared. So when you do that, everything here lies inside the square root sign. Alright, so I have this result. What is the motivation? The motivation is that we want to have this in the form sine x over x, okay, so that we can impute the results that the limit of sine x over x as x approaches 0 is 1. Alright, so going further, we can write that this is equal to the limit of 8x over, so at the end of the day, I'm going to have square root of x when I separate them, multiply by square roots of 6x plus 4 into sine x over x all squared. So the square roots covers everything here. So as x approaches 0, so that's what I have here. This is square root of x squared rather. Right, so from here I will now recognize that what this square root of x squared is not x, but it is modulus of x. So because of that, I'm going to have this to be the limit as x approaches 0 of 8x divided by the modulus of x multiplied by the square root of 6x plus 4 into sine x over x all squared, okay, as x approaches 0. So that is that about that. Alright, now so we have gotten to the main points, okay, or the main junction. So at this junction we have to now we have to recognize, of course we have recognized that this function, although it does not appear so, is actually a piecewise function. You know what a piecewise function is? That means it is defined quite differently, at different intervals. Alright, so Why is it so? Because we know that the modulus of x is defined differently depending on whether x is positive or negative. Okay, so we can see now, it is now obvious that this function is a piecewise function. So because of that, we're going to treat it as such. And see, don't forget this thing. Whenever you come across a piecewise function, okay, the limit of a piecewise function, please don't forget this, please never make the mistake. The limit of a piecewise function must be found in pieces, must be found in pieces, you don't write this in capital letter, in pieces. You should do it in different portions. See, if you have a piecewise function and you want to get its limit, say as x approaches 4, you should do it in pieces. What I mean by that is, first find out its limit as x approaches 4 from the right, then keep the answer, then also find out its limit as x approaches 4 from the left, then compare the answers. If they are the same, then the limit is equal to that value. If they are not, then the limit does not exist. Please and please, you must do that always whenever you come across a piecewise function. Don't do a direct substitution into a piecewise function. Please firstly define it in pieces and evaluate the limit in pieces. Okay, so for this now, naturally, if this were some number, let's say x were approaching 2, for instance, we would not have any problem if we interpreted this as x. If we interpreted square root of x squared as x, we will be fine if x was approaching 2, because in the neighborhood of 2, that is around 2, the modulus of x is simply x, because around 2 you only have positive numbers. But in this case, it will give you a very wrong number. Why it will give you a very wrong number in particular is because our x is approaching 0, and we know in the neighborhood of 0 we have both positive and negative numbers. So then we must recognize that this is some piecewise function. It has some piecewise effect, so that we don't fall into error. So when we did this in the last class, I talked about the fact that when we got to this point, where is it now? I think we did something like this in the last class. Yeah, when we got to this point, after factorizing, we recognize that this square root of x squared is actually modulus of x, okay, like we just explained again now. And then we recognized again that, but as x approaches infinity, x is far greater than 0. So because of x, is because we know that in the neighborhood of what x approaches, our modulus of x is going to be equal to x. Then it is fine to just interpret this square root of x squared as x, and then we did that here and got our results. Now we needed to firstly recognize this here. If we did not recognize it here, however, we would get a correct result. The reason is, whether we use modulus of x or we use x, we will be fine. But not recognizing it, where in this case does not pose a problem, is actually a potential problem, because you may be asked, maybe immediately after solving this now, you may be asked to find out what is its limit as x approaches minus infinity. That's another problem. If you already interpreted this to be x, then when x approaches minus infinity, you are certainly going to get a wrong result, because as x approaches minus infinity, x is far less than 0, and because of that, the square root of x squared is not going to be x, but it's going to be minus x. So if you just did a blanket interpretation from here that this thing is x, and you were asked to evaluate as x approaches minus infinity, you would certainly get a wrong result. Okay, so that is why you should first recognize it this way, then you will consider the neighborhood of interest. If the neighborhood of interest has all positive numbers, it's fine. Then you can interpret the square root of x squared as simply being x, that's positive x. Then if the neighborhood of interest is comprising negative numbers only, then you can simply interpret the square root of x squared as simply negative x, that's minus x. But when it is 0, then it has to be done in pieces, because around 0 we have both positive and negative numbers, as we have it here right now. Okay, so in this case we're going to say that therefore we find out the limit as x approaches 0 from above, okay, of this function of 8x divided by modulus of x into square roots of 6x plus 4 into sine x over x all squared. Alright, so we have this. So as x approaches 0 from above, we know that the modulus of x is x, because that is for positive numbers. Okay, for any positive number we know that modulus of x is simply x. So this is just going to be equal to the limit as x approaches 0 of 8x over x. Okay, so instead of modulus of x now we have x. Why? Because when x is positive, our modulus of x is x. So into square root of 6x plus 4 into sine x over x all squared. Alright, so I have all this right here. So from here, this can cancel this, it's fine. So then I can make a direct substitution. I'm going to have 8 over, this is going to be square root of 6 into 0, then plus, in this case I know already that the limit of sine x over x as x approaches 0 is 1. So plus 4 into 1. So then I have 8 over square root of 4, which is 2. You know, it cannot be plus or minus 2. I don't know with functions. Okay, so this is simply 2. So and this is 4. So that is the limit of this function as x approaches 0 from above. So going further, you will then say that the limit as x approaches 0 from below of 8x over modulus of x into square roots of 6x. Can you see what I'm writing? Okay. Alright, so plus 4 into sine x over x all squared. Alright, so this is going to give us, in this case, 8x over, so when x is negative, that's for values of x below 0. Alright, our modulus of x is going to be minus x. Don't forget, we have defined this in the past, that modulus of x, we have seen it in the past, that this is equal to x for x greater than 0, equal to 0, and it is equal to minus x for x less than 0. We have seen this in the past. Please go and revise if you still can relate with it now. Alright, so this is going to be minus x into square root of, so this is going to be limit as x approaches 0 or minus of this of 8x into over minus x into 6x plus 4 into sine x over x all squared. Alright, so x will cancel x. So at the end of the day, I'm going to have this to be the limit as x approaches 0 of minus 8. I'm moving the minus to that side now, into square root of 6x plus 4 into sine x over x all squared. Alright, so when you make a direct substitution now, we're going to get the result. This is going to be equal to minus 8 divided by square root of 6 into 0 plus 4 into 1, because the limit of this as x approaches 0 is 1. Alright, all squared, so that's still 1. So this is going to be equal to minus 8 over, this is 0, square root of 4 is 2, which is what? Minus 4. So as you can see, the limit as x approaches 0 from above is 4, whereas the limit as x approaches 0 from below is minus 4. So therefore the limit of this function does not exist. So we can write that since the limit of f of x as x approaches 0 from above is not equal to the limit of f of x as x approaches 0 from below, then what's the limit of f of x as x approaches 0 does not exist. Alright, so that's that about that. That is the And so that's how to solve problems like this. That is how to deal with piecewise functions. You should evaluate their limits in pieces. Find first the limit from above, then also find the limit from below, then see if the answers compare, compare the answers. If they are the same, then that is the limit of the function. If they are not, then the limit of the function does not exist. Okay, so let's take one more example on piecewise function. In this case, let's look at piecewise function that are actually obviously piecewise functions. Okay, so you know how to deal with them. All right, so look at this problem. We want to find out what this limit is. Look at this. We want to find out the limit of modulus of x minus 2 divided by x squared plus x minus 6 as x approaches 2. We want to find out what that is. Okay, we want to find out another example. We want to find out the let us say we want to find out, I'm trying to look for something simple. We want to find out the limit of the limit as x approaches 0 of x minus modulus of x divided by x. Okay, alright, so we want to deal with this, so you know how to deal with piecewise function. This is a piecewise function. You know, normally you expect that a piecewise function should be written in something in this form, something like having you to find if you're given something like f of x is equal to, let us say you have something like f of x is equal to, say, maybe x squared plus 1. Okay, when x is greater than 0 and it's equal to 3 when x is less than 0. You know, naturally you know that this is a piecewise function now, but you should also know that when you have this modular sign, you have the least integer or the greatest integer sign, whatever, you know it's some piecewise function. So then you have to be calm in solving in evaluating their limits. Okay, so the methods we have looked at before now, okay, you should know are actually suitable for non-piecewise functions. Alright, so immediately you can figure it out, or you get to a point where it becomes a piecewise function, then you know that you have to evaluate the limit in pieces. Alright, so let's quickly deal with this. So what do I mean by evaluating in the limit in pieces? This is what it means. Now let's deal with the second one first. We want to find out the limit as x approaches 0 of x minus modulus of x over x. Okay, so in this case you do not do a direct. If you do a direct substitution, you are going to get 0 over 0. Now you may even do a direct substitution and get some real figures. Now that does not necessarily mean that the limit is that value that you obtain. Never do a direct substitution for a piecewise function. I repeat, never do a direct substitution for a piecewise function. Please always break it down into pieces, then evaluate from the right, from the left, then compare their values. Okay, so in this case we know that the limit we know that the modulus of x that we have here has some values around 0, okay, which are different. Okay, so we will first say that our f of x is equal to x minus modulus of x over x, which will be equal to, depending on the value of x now, when x is greater than 0 or equal to 0, we're going to have, when x is greater than 0, we're going to have this to be x minus x, because when x is greater than 0, modulus of x is x. Okay, so this is going to be x minus x over x when x is greater than 0. Now going further, when x is 0, what is going to happen? When x is 0, we are going to have 0 minus 0 over 0, which is undefined. So we say that this is what? Undefined. when x is equal to 0. It's okay. Then the third one, when x is less than 0. You know, when x is less than 0, modulus of x is going to be minus x. So when x is less than 0, I'm going to have x minus modulus of x, which is minus x all over x when x is less than 0. So this is actually the function we've been given. We can simplify further. So when you simplify, you're going to have this to be x minus x is 0. 0 over x is 0. So I have 0 whenever x is greater than 0. And then we know that this is undefined when x is equal to 0. Then this is going to be x minus x. X minus minus x is x plus x. That's 2x. 2x over x is 2. So this is equal to 2 when x is less than 0. So this is the function we have been given. It was not given, it was not written in this piecewise form this way, but you should recognize it that it is a piecewise function on citing the modulus figure, modulus sign. Alright, it can also be the least integer or the greatest integer sign, that's as we have seen before now. Alright, so this is the function we want to deal with. This is the function f of x. So we want to find out its limit as x approaches 0. So this is how to do it. We'll first find out the limit of f of x as x approaches 0 from above. That's what I mean by obtaining or evaluating the limit, of finding the limit in pieces. Alright, so we want to find out what its limit will be as x approaches 0 from above, and that will be equal to, so as x approaches 0 from above, we look at how is the function defined. So we know that as x approaches 0 from above, that means we are interested in the values of x greater than 0, of course, and very close to 0 but greater than 0. So very close to 0 is a relative thing. It can be something like 0.0001 close to 0, but it's still greater than 0. Alright, so we look at the function, the definition of the function, and see that okay, for values of x greater than 0 and around 0, how is our f of x defined? So in this case, for values of x greater than 0, our f of x is simply 0. So what we have here is simply the limit of 0 as x approaches 0. Okay, as x approaches 0. You know why I'm not putting from above any longer? I already, took that into consideration in obtaining what the function is. Okay, when x is slightly above 0. Alright, so this is simply 0. Okay, then you look at the second portion, the limit as x approaches 0 from below of f of x. That is for values of x less than 0, of course, in the neighborhood of 0 but less than 0. Okay, so we look into the function again. For values of x less than 0, our f of x is defined as 2. So what we have here is simply the limit of 2, which is some constant function, as x approaches 0, which is equal to 2. So that is that. So as you can see, the limit of f of x as x approaches 0 from above is not equal to the limit of f of x as x approaches 0 from below. Okay, which means the limit of f of x as x approaches 0 does not exist. Okay, so that's that about that. Can your calculator do this? Yes, I think so. The calculator has the absolute function. Alright, so you can enter it on your calculator, maybe in form of verification in this case. So you're going to have alpha x minus modulus of x. So this is modulus function. You see it here, it's called ABS. This one ABS means absolute value function. So you can put shift ABS, so it already gives you that. Then alpha x divided by alpha x. So you can calculate when you have a value slightly greater than 0. It's already here, so you're going to have this thing to be 0. When you have a value slightly less than 0, minus 0.001 or whatever, it's going to give you 2. Alright, so you can see that the limit, the right hand and left hand limits are not the same, so the limit does not exist. Okay, so that is that about that for question B. Alright, so let's solve question A. So for question A, let's do it on another page. For question A, we have to evaluate as x approaches 2 the modulus of x minus 2 divided by x squared, let me check, plus x minus 6. Sorry, this is modulus x squared plus x minus 6. Alright, so again, recognizing these as a piecewise function, then we are going to define it this way. We know that this modulus of x minus 2 is going to be equal to x minus 2 is going to be equal to x minus 2 when x minus 2 is greater than 0. You know, this just follows from our definition of the modulus function. We know that modulus of x is equal to x when x is greater than 0. Alright, when x is greater than or equal to 0, and then it is equal to minus x when x is less than 0. Okay, you can see that already. So in this case, our x, which is what we have in the inside the modulus sign or modulus function, is being replaced technically by x minus 2. Alright, so that means the modulus of x minus 2 will be x minus 2 if x minus 2 is actually greater than or equal to 0. Okay, if you like. Alright, then you can say that this will be equal to minus, just like we have minus x when x was inside here. So this will be equal to minus of x minus 2 if x minus 2 is less than 0. So we can simplify this further. This is going to be equal to x minus 2 if x is greater than or equal to 2. We don't want to simplify this, and this is going to be equal to 2 minus x. And when you open the bracket, when x is less than 2. Alright, so that is what you're going to get. That is the meaning of this thing. Then therefore we can write that f of x, which is the function we are given in this case, is equal to, this will be equal to x minus 2. Now for this interval, we already know what this is going to be. It's just going to be x minus 2. So what we have is just going to be x minus 2 divided by x squared plus x minus 6 whenever x is greater than or equal to 2. And then it will be equal to 2 minus x divided by x squared plus x minus 6 whenever x is less than 2. So I hope you got that. Alright, so it's as simple as that. Alright, so this is what we have. Then we are interested in the limit as x approaches 2. So we have to look at the limit as x approaches 2 from below, look at the limit as x approaches 2 from above, then compare the results and decide. Right, so in this case we know that the limit, we find out the limit now in pieces. The limit of f of x as x approaches 2 from above. Let's do from above first. You can do anyone first anyway. So it's going to be equal to what? Now I already know what my function f of x is when x is above 2. So I know it is just going to be this. So this is going to be equal to the limit of x minus 2 over x squared plus x minus 6 as x approaches 2. Alright, so that's what I have right here. Then you should see that when you substitute, you're going to get 0 over 0. You can actually factorize this. You can factorize this is x squared, you know, so you have minus 6, you can have plus 3 and minus 2 right here. So you can factorize. So when you do that, I'm going to have this to be equal to the limit as x approaches 2. You know why I'm not including plus here? Because I already took into consideration the effect of this plus in that it determines what my function would be like. So I already took that into consideration in determining this. So I simply want to get the limit of this as x approaches 2. Okay, so I have this to be x minus 2 divided by, you know, when you factorize this, you should get x plus 3 and x minus 2. Alright, so this is going to cancel this. Then as x approaches 2, you're going to have 1 over 5. So this is going to be, when you substitute, you have this here. So this is 1 over 5, and that is the limit of the given function as x approaches 2 from above. Then we can also find out the limit of the given function as x approaches 2 from below. So that is going to be what? As x is less than 2, we have the function to be defined this way. So we can write that as the limit as x approaches 2 of, this is going to be 2 minus x over x squared plus x minus 6. Alright, so again, when you substitute, you're going to get 0 over 0. You can, however, make a factorization to obtain this to be equal to the limit as x approaches 2 of minus into x minus 2 divided by x minus 2 into x plus 3. Alright, so when you do that, this will cancel this, so I'm going to have minus, when you make a substitution, minus 1 over 5. Right, so you can see the limit from above is 1 over 5, the limit from below is minus 1 over 5. So because of that, the limit of f of x as x approaches 2 from above is obviously not equal to the limit of f of x as x approaches 2 from below, and therefore the limit of f of x as x approaches 2 does not exist. So you can equally verify that with your calculator. Alright, so while you want to do that, you can have something like this. Let's just edit this directly. So I have x minus 2 alpha x minus 2, the modulus, and I have x squared plus x and minus 6. So that's what I have there. Then I want to find out, calculate around 2 from above, that's 2.0001 for instance. So it's gonna give me 0.1999996. Okay, so that is what do you call that now? That's gonna be 0.2, okay, approximately, which is 1 over 5, like that we got right now for x approaching 2 from above. Then for x approaching 2 from below, for x approaching 2 from below, we're going to have 1.9999 something. So it's still going to be, this one is going to be minus 0.2, as we have seen, it's minus 1 over 5. Alright, so that is that about that. This is how to deal with piecewise functions. You define them properly to be able to visualize them as they are. Then you evaluate the limit in pieces. Okay, so once you are done with that, then I think we are good to go with limits. So in the next class, I think that should be the last class on limits, we're going to be looking at L'Hopital's rule, L'Hopital's rule, and how to use it to simplify some other indeterminate forms. We have so far actually devised a lot of means to actually solve for indeterminate forms, okay, but they are actually simpler, or I think faster. You get a faster approach and simpler approach, and specifically or particularly when you have transcendental functions. I think you should remember now what transcendental functions are. If you can't, go back and watch those videos where we discussed functions at the beginning. Alright, so I guess that is that for today. So I'm going to give you some assignments that have to do with limits of piecewise functions, so you know how to deal with them. Alright, and then we'll move on from there on to L'Hopital's rule in the next class and look at the indeterminate forms. Okay, we're going to be looking at these indeterminate forms, the different indeterminate forms you can come across, which so far these are the common ones you can come across. You can come across 0 over 0, okay, you can come across infinity over infinity, indeterminate. You can come across 0 multiplied by infinity. You can come across infinity minus infinity. I think at almost every stage, or at some stage, I've explained almost all of them why these things are indeterminate. Okay, it is still true that 0 multiplied by anything, so to speak, is 0, of course, but in this context we're dealing with limits. This thing is not exactly 0, it is just approaching 0. This is not exactly infinity, it's approaching infinity. So then the actual value of this depends on how fast this approaches 0 compared to how fast this approaches infinity. So at the end of the day, we will have to say this is indeterminate from the particular result that got us to this place, or from the particular process or method that got us here. Then it means we will have to devise another means to actually see a limit that takes into consideration some rates of change, so that we can actually compare how well or how fast this approaches 0 compared to how fast this approaches infinity. And that is what the L'Hopital's rule actually sorts for us. Okay, so that is 4 and 5. We can have 0 raised to power 0. We can have infinity raised to power 0. Then we can have 1 raised to power infinity. We can also have infinity raised to power infinity. So any of these forms are indeterminate forms. So is infinity raised to power infinity indeterminate? It should be 0 raised to power infinity. It should be 0 raised to power infinity. I think this should be 0 raised to power infinity. Infinity raised to power 0 raised to power infinity. It's indeterminate. Is that correct? Yeah, okay. Don't worry, we get to see how to deal with cases like this in the next class, from L'Hopital's rule. Alright, thank you for your interest in Max Engineering tutorials. We'll see you in the next class. Hopefully by the end of the month we have another test, hopefully. Okay, so you can see that we are still far away from everything you already did before the lockdown. I mean, you already got to, what is it now, sequences before the lockdown in the school lectures, and here we are still dealing with limits. So please take these classes very seriously, irrespective. We don't know when school will resume yet. Nobody knows. This can no longer predict, but let's just stay alert. Okay, so anytime we ask to resume, anytime you are called upon to resume, you're still okay. I mean, academic wise, you're still you're still alert academic wise. Okay, so that's that about it. I'm going to give you questions on this, and thank you.